Let's take a look at another example. We're going to consider some current carrying loop with current I2 that's placed parallel to an infinitely long current carrying filament with I1. So we see that drawn here below. And we want to determine the force experienced by our current carrying loop from this current I1 in our infinite filament. And so notice in this case, the infinite filament is given on the z-axis. We have some distance between that filament and our current loop with I2 of rho naught. And we have dimensions of our current loop, so we have it has a width of A and a height of B. And so what we're going to see in a little bit is that it turns out that it's kind of handy having that infinite filament along Z, because our local definitions for rho and phi turn out to be our global definitions in cylindrical coordinates. And keep in mind that this is something that we could do. We could define our axes or our coordinate system to fit the problem. In this case, it just happens to be given this way, but of course that's something that we could do in real life if we actually wanted to. Okay, so looking at this, it might be tempting to say we had our three cases where we could experience force due to magnetic fields, and here we have two current carrying elements. So we could say, let's look at case let's look at case 3, which was the case of force between two current elements, because of course we have two current elements here, so why not? So force between two current elements, but what we're going to see is it's actually easier in this case to consider our second method. So it's easier to consider case 2, and remember case 2 was just force on a current element. So force on a current element which was present in the presence of some magnetic field B. And so the reason is because we already know an expression, a relatively simple expression, for the magnetic field due to some infinitely long current carrying filament. So we know that for this current carrying filament, we're going to have some magnetic field given by B1, which is equal to mu naught times the current in the filament, which is I1, divided by 2 pi times rho. And again, rho is going to be the locally defined perpendicular distance. In this case, it just happens to coincide with the rho direction as we see here defined in our axis right there. And that was in our phi direction. And to be general, we said that our phi direction was equal to our u of L, which is the direction of the current, cross with the u of rho, which was the direction of the unit vector in the perpendicular distance from the filament to the point of interest. But again, in this particular case, those phi and rho directions are going to align with our general definitions for cylindrical coordinates. Okay, so if we come back up to our drawing then, we can use our right hand rule to get sort of a rough idea of what our magnetic field is doing. We put our thumb in the direction of I, and what we see is on the left side over here, our fingers are curling out of the page, so our magnetic field B1 is going to be coming out. And over here on the right side, we know that that's going to be going into the page, so our B1 is going to be going in. So something like this. And so we can kind of use that to get a rough idea as we're sort of approaching the problem, and then again at the end to sort of double check. Okay, so if we're going to use this case 2 then, let's go to our general equation for this case 2. So we said if we have some current element in a magnetic field, then the force on that current element was F sub L, and that was equal to the current in the element, in this case I2, times the integral around the closed path L of dL2 cross with, in this case, B1. Okay, so we come back up here and we're looking around this closed path L, and we need to figure out dL2. And so it should be pretty obvious to see that we can't characterize a single dl along this entire path. So instead, what we can do is we can break this up into 4 smaller paths. So we can say we have path 1, which is going from here to here, and along that path we're going to have one constant dl. We'll have some second segment, which will have a constant dl in the rho direction, a third segment over here, which is again going to be changing in z, and then finally a fourth segment right here, which is changing in rho. So what we're going to do then is we're going to break this up, and instead of saying FL, we're going to say really that's just the sum of 4 paths or 4 forces. So we're going to have F1 plus F2 plus F3 plus F4. And so each of those is going to be the force along those 4 segments that we described above, and they're each going to have a different differential length dl. So let's take a look at each one of those. So let's start with that segment 1. And so let me scroll up for a second so we can look at segment 1. So remember, segment 1 is right here. So we see our differential length is going to be changing in z, and we're starting. So we want to note the current direction here. So it's starting down here at, we can call this our z equals 0. Again, this is something, if it wasn't given to us in the problem, we could sort of define our coordinate system to fit that. And it's starting at 0 and it's going up to some height of b. And so really it could be starting at some z naught and going to z naught plus b, and we'd see the same result. Okay, so coming down here, sort of putting all of that on the page, we've got our dl2 is equal to dz in the z direction. And as we said, our z is equal to 0 initially, and it's going to b, so that's going to be our limits of integration. So now we just come and plug into this more general equation here. So we can see that our f1 is going to be equal to our current I2, integral from z equals 0 to b of our dz in the z direction, cross with our b1 equation, which we had up here. So that was our mu naught times I1 divided by 2 pi, and now the perpendicular distance rho for this first segment is just going to be the constant value of rho naught, because everywhere along that segment we're just the same perpendicular distance of rho naught away. So coming down here, we're going to put rho naught for that perpendicular distance, and again that is in our phi direction. Okay. So we can pull out some constants. So of course we have here pretty much everything is going to be a constant in this case. We're going to have I2, well, let's put our mu naught out front, mu naught I2, I1 divided by 2 pi rho naught, because rho naught again is just a constant distance there. And then we have the integral from z equals 0 to b, and we're going to have some direction, so z cross phi, we can do our right hand rule, and we see that's going to be in our negative rho direction. And again, these are our global phi and rho just because of how we've defined the problem. And of course we have our dz coming from our dl there. And so of course what we can see if we do that integration, we're just going to get z evaluated between 0 and b, which ends up just being b. So we get a final value for our force on segment 1, which is going to be equal to mu naught times the product of those two currents, I1, I2. We also have a b in the numerator from that integration, and then 2 pi rho naught, and all of that is in our negative rho direction. And so we can stop for a second and think about what that actually means. So coming back up to our segment, that means that, or our loop rather, that means that this segment right here is going to be experiencing a force in the negative rho direction, and of course that is proportional to the current I1, the current I2, and inversely proportional to the distance rho naught. Okay, so let's look at our segment 2. And so while we're up here, let's just go ahead and point out a couple things. So we see now our differential change is going to be in the rho direction. We see we're starting at a value of rho naught, and we're going to a value of rho naught plus a. So let's come down here and write all that down for segment 2. So segment 2. Okay, so we said our DL, let's see, so DL2, so I should have called this one up here DL1. Not sure how that slipped past me there. Okay, so our DL2 though is equal to d rho in our rho direction, and okay, so sorry, all of these are DL2. I'm just recognizing my mistake here. So all of these are DL2 because we're saying it's just general DL2 because we're on the circuit with L2. So let me change this back to DL2. Okay, so sorry about that. So our DL2 is d rho in the rho direction. And again, as we said, our rho is starting at rho naught, and it's going to an ending value of rho naught plus a. All right, so let's do our general force equation again. So now we're going to call this F2, our force on the second segment, which is equal to I2 times the integral from rho equals rho naught to rho naught plus a. And we have d rho in our rho direction for our differential length, and that's being crossed with the same b we used before, so mu naught times I1 Let's make that a little bit cleaner, times I1 divided by 2 pi. And now in this case, I'm going to leave this as a variable rho. And the reason is because if we look at segment 1, our rho was always constant. We were always the same distance away. But here, of course, our rho distance is going to be changing depending on where we're at on that segment 2. So we want to leave that rho as a variable. And of course, that is in our phi direction. And so we can again pull out all of the constants, everything except for rho. So we have mu naught times I1, I2 divided by 2 pi. Our integral is going from rho equals rho naught to rho naught plus a. And the only thing left in there is going to be our d rho over rho. And our direction in this case is going to be our rho direction crossed with our phi direction, which gives us the positive z direction. Okay, so doing that integral, you might recall that, of course, the integral of 1 over x, or in this case 1 over rho, is just going to be the natural log. So we find that our force on our segment 2 is equal to mu naught times the product of our two currents, I1, I2, divided by 2 pi, and then we have the natural log. And so using log properties, it would be log of rho naught plus a minus log of rho naught, and we can change that into log of rho naught plus a divided by rho naught. And again, that's going to be in our z direction. Okay, so there's our equation for force 2. And so again, let's sort of come back to our I2 current loop and look at exactly what that means. So we can note that it's sort of changing. We have this inverse relationship to our rho naught. And so what we see is that's in the z direction. So we're going to have some force up here, which is pulling this segment in this direction here. Okay, so now let's look at segment 3. So on segment 3, again, our change is going to be only in the z direction. We're initially starting at a height of z equals b, and we're going back down to z equals 0. So let's come down and fill out everything for our segment 3. Let's come down here to a new page. Okay, so segment 3. So again, in this case, our dl2 is going to be equal to dz in the z direction. And so you might be saying, hold on, we were going down. Why is it just in the z direction and at negative z? And so remember, with our line integrals, this dl is always going to be positive, and then we're going to let our limits of integration take care of any negative sign. So we're going to say z is going from b to a value of 0, and what we're going to see is that's going to introduce our negative direction. So our f3 is then equal to our I2 times the integral from z equals b to 0 of dz in our z direction cross with our b naught, or sorry, our b1, which is mu naught I1 divided by 2 pi. And now again, we have a constant rho, a constant perpendicular distance, but now it's going to be rho naught plus a. And that's going to be the same distance no matter where we're at on segment 3. So coming down here, we're now going to have rho naught plus a for our rho distance, and that is in our phi direction. And so again, we can pull out all of those constants. So we're going to have mu naught I1, I2 divided by 2 pi, and then our rho naught plus a is also a constant value, so that can come out. And we have the integral from z equals b to 0 of dz, and our direction is z cross phi, which again is going to be negative rho. And what we see is when we do this integral here now, again, we get z, but because it's evaluated from b to 0, we get a negative b. And so that negative is going to cancel out with the negative sign here in our rho direction. So ultimately we get that our f3 is going to be equal to mu naught times I1 times I2 times our distance b. And I don't have the negative because we're going to cancel that out and just say this is in our rho direction. And that's divided by 2 pi times rho naught plus a. Okay, so again, let's come back up to our drawing, and we see this is going to be in the positive rho direction. So coming back up here to our segment 3, we see that this has some force in this direction here. All right, so then finally for segment 4, similar to segment 2, we're changing only in rho direction. Now we're starting at rho naught plus A, and we're going to rho naught. And just like with segment 2, note that our rho is varying as we're moving along this segment, so it's going to be further here and closer here, so we want to keep that rho as a variable in our equation for B1. So let's come down here to segment 4. Okay, and so our dL2 is going to be equal to d rho in our rho direction. So again, note we have a positive differential length, and our limits of integration are going to take care of any signs that we need. So we're going from rho naught plus A to a final value of rho naught. So plugging into our equation, we then have that our F4 is equal to I2 times the integral from rho equals rho naught plus A to rho naught of our d rho in the rho direction cross with mu naught I1 divided by 2 pi, and again our rho is a variable, so we have just a general rho in our phi direction. So we can pull out all of those constants, so mu naught I1 I2 divided by 2 pi, integral from rho equals rho naught plus A to rho naught, and we're left with again our d rho and divided by rho. Our rho direction crossed with our phi direction is going to give us again our z direction, same as we saw with segment 2. And now what we're seeing is we have sort of again the same natural log when we integrate, but we're going to have rho naught in the numerator and rho naught plus A in the denominator. So we can say our F4 is going to be equal to mu naught, product of the two currents, I1, I2, divided by 2 pi, natural log of, in the numerator we have rho naught, denominator rho naught plus A, and that's going to be of course in our z direction. Now what we can do here is we can use some log properties, and so remember we said we had log of A minus log of B is equal to log of A over B. Well, if I multiply this side by -1, that essentially just switches the order, which is the same thing as coming over here and switching which one is on the top. So this would be then B over A. So if I do a similar thing here, what I can say is this is going to be negative mu naught I1 I2 divided by 2 pi natural log, and then I'm going to switch the order so to have rho naught plus A divided by rho naught in our z direction. And so why would I want to do that? And so the reason is, now if we compare this to our F2 result, we see we have this same term, it's just going to be negative valued. So we have that same log of rho naught plus A divided by rho naught, and it's just in the opposite direction. And so let's come back up here and let's add our final force here. So we're going to have a force here in the negative z direction. And so because those magnitudes on 2 and 4 had the same, or the forces on 2 and 4 had the same magnitudes, our F2 and our F4 is going to cancel out, and we're going to be left with only forces, our net force is going to depend only on 1 and 3. And what we'll be able to see from the equation when we write it out is that, of course, our force on segment 1 is going to be stronger because it's closer to our line segment I1. Okay, so now we're basically just coming back to this equation we started with, and we're saying we want this overall force on the circuit, so we're going to sum these. And so we said that our F2 and our F4 are going to cancel out, and so we're just going to be left with F1 and F3. So we can come down here and let's write our final force on the line on our circuit L2, and that's going to be equal to, so both terms had the same mu naught times I1, I2 times B, so the height of the circuit, divided by 2 pi, and for our first term we had 1 over rho naught, and so we're going to put all of this in the negative rho direction. And so what that means is I'm going to adjust this segment 2 a little bit. So if I want this to be in the negative rho direction, I'm just going to put a negative sign out front. But I've already factored out all of that, so I'm going to associate that negative sign with this 1 over rho naught plus A. So I'm going to write this as -1 over rho naught plus A and that is in our negative row direction. So that would be our final answer for the force on that current carrying segment I2 due to our infinite current carrying filament with current I1. And so again, as we noted above, we see that this value is going to be larger because we have a larger denominator here, which is going to make that second term smaller. So we're going to have the force on the inner segment, segment 1, is going to be stronger than the force on that outer segment. So let's say instead we were asked to find the force on that filament carrying I1. So how would we figure out the force on this segment right here due to our segment I2? Well, basically we just go back to Newton's third law and we say for every action there's an equal and opposite reaction. So if our I1 creates this B, which is pulling and pushing our I2 in certain directions, then there's going to be an opposite and equal force on our wire. So we could say the force on the wire, which is carrying I1, is just equal to negative FL. So simple as that.